Good afternoon, everyone. I want to welcome you to my lecture today. Before I get started today, I got some announcement to make. Of course, tomorrow you're actually going to see result for midterm 2. I completed the grading yesterday, and they will be uploaded to Canvas today. And of course, because we are counting down to the final, I'm actually going to release a statement today on announcement section, where I'm going to tell you chapters in the textbook that will be covered in the final. Does that make sense? And of course, before the end of the week, I'm going to release our final practice questions. Okay, so today we got two materials that we want to review. This is going to be the first one. Okay, um, we call it sampling with T and F distributions. Of course, before now, we've worked with sampling with normal distribution, right? Where we actually conduct a repeated experiment where we have opportunity to see uh, the possible values means can take, but we got some situation whereby we may not be able to go by way of sampling with normal distribution. So a situation where the sample size is small, okay, or the population standard deviation is not given, okay, then it is going to be appropriate to sample with T distribution instead of with normal distribution. Of course, how am I going to know if my sample size is small? Of course, the central limit provided that, provided a threshold for large sample. The large sample is 30 or more. Okay, the small sample will be less than 30. Does that make sense? That's what small sample means. So I'm going to walk you through that. I'm also going to walk you through how we're sampling with F. Okay, so let's get started. Um, you know, if you take a look at what you are seeing here, okay, if you take a look at what you're seeing here, initially equal x minus mu over standard deviation, okay, over standard deviation divided by square root of n, okay. Now when you take a look at that first one, okay, that is a situation where we are working with a large sample. According to central limit theorem, the sample size is at least 30 and population standard deviation sigma is known. Situation where we are now working with large sample and maybe the sample size is less than 30 and the population standard deviation is not given, then we're actually going to use this guy. It's going to be T distribution instead of Z. So it would not be appropriate to use a Z in a situation where the sample size is small and when the population standard deviation is not given. And as you can see here, situation where population standard deviation is not given, we're actually going to replace that with a sample standard deviation. You can see S, okay, S represents sample standard deviation. The sigma up there represents population standard deviation. So they are not the same. Okay, I just need to take note of that. Now, how do we actually formulate T distribution? Do you know T distribution actually come from, having come from a Z distribution? Take a look at this in the numerator. What you see in the numerator is actually Z, right? It's actually Z, right? Okay. Now, when I divide, you remember we've done distribution function of random variable, like I started with a random variable x with a defined probability distribution, and I want to figure how the probability of a new variable that depends on the old variable. Of course, we did that in this class. Now, if z, okay, equal to that numerator, if I divide that by this, if I divide by square root, it's like I'm dividing by a ratio of sample standard deviation to sample variance, because S square is sample variance, sigma square is population variance. When I find the square root of that, well, I'm talking about the square root of that denominator, that is going to be the ratio of sample standard deviation to population standard deviation. And let me tell you this, I need you to pay attention now. Do you know that situation where n is large, according to central limit theorem, that's what I circle here is going to be 1. You know why it's going to be 1? Because there's not going to be any difference between sample standard deviation and population standard deviation when sample size is large. But if the sample size is not large, if it is small, and how small, what is the threshold? If it is less than 30, okay, then there's going to be a difference between sample variance and population variance. Does that make sense? Now, if that difference exists, then I'm actually going to have a new distribution that actually going to call T distribution. So which means T distribution come from a Z distribution. When I divide a Z distribution by by that guy, I'm actually going to have a T distribution. Now you now know that the numerator here is actually Z. Okay. And let me also tell you, mathematically speaking, we can rewrite this guy to be the same as this, which means S squared, the sample variance, divided by population variance, okay, equal V divided by N minus 1. When I solve for V, okay, when I solve for V, I'm actually going to have this guy. If you solve for V, I'm actually going to have this guy. And do you know what V represents? That's a chi-square. You remember the other time when we were dealing with a chi-square, I told you a chi-square statistic is n minus 1 multiplied by sample variance divided by population variance. If I now want to tell the world about how we formulate T distribution, I'm actually going to tell the world that T distribution actually come from Z distribution and a chi-square distribution, because Z, okay, from normal, and V is a chi-square, which means T distribution can be traced to two distributions, to chi-square distribution and to a standard normal distribution, because Z is a standard normal distribution. Okay, now I just wanted to take note of that. Now the n minus 1 is the degree of freedom. Whenever I'm working with a chi-squared, we use degree of freedom n minus 1. If we are also working with T, okay, we're also going to use degree of freedom. Now the question is, what is degree of freedom? How do I know the degree of freedom is going to be n minus 1? I need you to listen now. The degree of freedom is actually the numbers of independent pieces of information that we allow to vary. If I have a sample size, whenever we estimating parameter using sample information, we normally impose a constraint. Does that make sense? Maybe I want to figure out the sample mean. I want to find mean. We always impose a constraint. The constraint is that, the sample mean that we want to find must actually obey certain condition. Now, when I find sample mean, the sample mean is actually, summation x divided by n. And you know what? What is summation x? Summation x will be equal n x bar. Do you know that? NS bar? Do you know that the fact that if you have n data, like you have your sample size is n, and the degree of freedom is talk about the numbers of parameter, or the numbers of values that we allow to vary. Okay, if I have 10, okay, it's not going to be 10 that we're going to allow to vary. You know why it's not going to be 10? It's going to be 9, because we have imposed a constraint that if I sum them together, if I sum the observation together, it must be equal to nx bar. And NS bar is 1 out. It means you have deducted 1 out of 10. Is now going to be 9, which means it's not going to be 10 that will be allowed to vary anymore. It's going to be 9, because you've already imposed a constraint. Imposing a constraint will reduce the numbers of free parameters by 1. And that is why it's called degree of freedom. The numbers of degree of freedom, and it's always going to be n minus 1. Does that make sense? Okay, now if I want to look at T distribution, when you take a look at this guy here, okay, this is a T statistic. Okay, if I want to talk, do you know that if I give you this in exam, okay, if T equal to this, right? If T, give me 1 second. Please, I needed to pay attention. If T equal to this guy, right? T equal to this guy, okay? And I ask you to get me the distribution for T, okay? Now, if you want to get a distribution for T, okay, we have Z and V, right? Now you need to be able to know Z. What is the F of Z? F of Z is standard normal. It's actually going to be 1 over. Let me quickly do this. Okay, so T, please pay attention. T equal Z over V over V over V. This is chi squared. Let me just say divided by n, or divided by the degree of freedom. Don't let me use n minus 1. For instance, give me 1 second, because this is what I want to derive. This is what I want to derive. Okay. Okay. Now, if this is what I want to derive, take a look at this. This is where it's gonna look like. T equal to that. Z, the Z that you see is standard normal distribution. Okay, standard normal distribution. So Z follow normal with this. The standard is going to be F of Z equal 1 over square root of 2 pi exponential raised to power this. That is F of Z. Then V follow chi squared. Okay, see, this is a small v. Don't convince this. This small v here is the degree of freedom, the n minus 1. But I'm going to call it that small v. Okay. Now, with this degree of freedom, now In order for this not to confuse you, let me use instead of small v so that you don't confuse this with this. This is a chi-squared. This is the degree of freedom. Maybe I should call this R. Let me call this R. This that small one R. Okay, and you know f of v will be v raised to power. You remember from a gamma distribution. Let's first remember something from a gamma. F of v equal v raised to power alpha minus 1 exponential raised to power this divided by gamma alpha beta raised to power alpha. Now, if I want to change to chi-squared with v degree of freedom, you remember that I said the other time when alpha equal r over 2 and beta equal to 2, right? So this is going to be r over 2. This is going to be 2. And gamma alpha r over 2. Then 2 raised to power r over 2. Now, I'm using v, right? Then this v here, now this is a chi-square distribution. Now, this is what happened. I want you to derive this guy. H of t, that was why t equal to this. Now, if t equal to that, you're actually going to create artificial variable. This is a t, you're going to create something here. What you're going to create will be the variable in the denominator. So I'm actually going to say maybe I can write f equal to v. Does that make sense? You remember what we did? This is, I want to generate t, right? And I got two variables. I can't go from two variables to just one. You create artificial variable. Now, if you take a look at this now, then you find the inverse. The way you normally do, find v, okay? And here find z, find the inverse. After finding the inverse, then you need to first find a joint, okay? What is going to be the joint? You need to find the joint of z and a and v. What are you going to do? You're going to multiply this by this so that you'll be able to get what? You'll be able to get f of z and v, right? Why h is equal to f of z multiplied by f of v. So when you now get the joint, what are you going to do? You find the inverses here and set up a Jacobian matrix. You remember what we did before? Set up a Jacobian matrix, then plug in wherever you see those inverses here. Then at the end of the day, you actually going to get g of t and f. When you get g of t and f, what are you looking for? You're looking for that of t, right? You're going to integrate this guy with respect to f, which means you're going to integrate that guy out. So when you do that, this is what you're going to get. This is a t distribution. Okay? You can try and practice that. You've done that before. You've done something that relates to that before. And like I said, v here is the degree of freedom. Okay, now, these are the two basic statistics that we always want to talk about, the sample mean and the sample variance. But I need you to pay attention to this. In the sample variance, we are dividing by the degree of freedom. Why not by n? We are dividing by the degree of freedom because that will make a sample variance unbiased estimator of a population variance. I'm going to say that again. Why are we dividing sample variance by the degree of freedom, n minus 1? Because that is dividing this by n minus 1 will make sample variance to be unbiased estimator of a population variance. Does that make sense? Okay, now that is that. I'm going to quickly walk you through an example now. Okay, if you take a look at, let me tell you this. If you take a look at this particular distribution here, this is what we use to simulate values in the t-table. We're going to be checking t-table. Okay, the T table we're going to be checking, under certain degree values for degree of freedom. So this is what they use to simulate that. Now take a look at this now. I take a look at example 8.8. The T value with V equal to 14 degree of freedom that leaves an area of 0.025 to the left. And of course, when it leaves 0.025 to the left, it will automatically leave 0.975 to the right because the total area under a curve equal to 1. Does that make sense? Now, do you know that if I want to check that in the table, I need you to take a look at this. In the T table, we don't have these big values. We only have we have the level of significance, 0.025 and the line. So if I want to check for this is going to be the same thing as negative of the other one. If you take a look at what you have here, this is more, you remember the other time I told you, we got a formula, okay? Where is it going? We're going to say T1 minus alpha equal negative T alpha. You see that? Okay. T1 minus alpha equal to negative T alpha. So if you want to check from a T table, what you're going to do, you're going to check under the degree of freedom 14 and check is at 0.05 level of significance. That will give you 2.145. But you know, this negative is because of this negative. Let's say they want me to check for this guy. There's not this guy in the table. And we have to check for this guy. Whatever I get, I put a negative on that. Is there anyone who doesn't know how to check from T table? Is there anyone? Okay, so the T table, you can check it at the back of your textbook. Now, that is how that is done. Now, what if they ask you to find this? Find the probability that T lie between this and this. Okay? If I want to find this guy now, you know, T is 0.05, leave an area is 0.05 to the right, and T and that leave an area is 0.025 to the left. How do I know? Because this is the negative side. This is the left side. This is the right side. You know, you should always look at it like this, right? You see, where's my left? My left hand touching. Where's my right? Can you see that? And that's explained that. Okay, now if I have that guy now, what I'm gonna do, you know, like I said, I'm working on this guy. Okay, now I need you to pay attention and look at this. When the leaf is zero, you know, when the leaf is 0.05 to the right, and that, then we're actually going to have 1 minus 0.05 minus 0.025, which is going to be equal to that. And if this is what I have, then I can boastfully tell the world that everything here is just 0.925. Okay, so because it just subtracts. Like here with the, you know, if you want to solve something like this, a problem like this, you don't need degree of freedom. But the one up here is asking you to find a T value. If you want to find a T value, you need a degree of freedom to find a T value. If you want to solve a probability, you don't need a T value. You don't need a degree of freedom. Now, this is what we got for that. Okay. Now, there's another problem. At times, take a look at this. Take a look at this. The probability of T lie between K and that equal to 0.045, then they want you to determine your K. If you go back here, you know, when you were given this, we're able to get this. But what if in a situation where one of this is missing and they gave you this? How do we go about it? We're going to go about it I need you to pay attention on how we're going to go about it. Now, if you look at the question, it says find K such that the probability of T lying between that equal to that for a random sample of size 15 selected from a normal population. Okay. Now, if you want to do that, I need you to pay attention to the shape, to what you're giving here. Take a look at this. I need you to look at the shape. Okay. If you look at that very K, right? If I do like this again, that is to my left side. And that's why we're talking about this side. Do you see that? We're talking about this side. Now, if we're talking about that side, they've already given us that the whole thing is going to be 0.045. And if that's happen, if you take a look at what I have inside here, okay, why do I have a 0 point? Can somebody tell me for extra credit? Why do I have a 0 point? Oh, okay. I've already put it here. So, okay. So let me just, I'm not going to say for extra credit anymore. Now take a look at this. Okay. 0.045 will be equal to 0.05. How do I know is I'm actually going to subtract that from that? Because alpha, do you know the standard alpha level of significance? It is 5%, 0.05. Okay, now if I have a 0.045, then, and I know the alpha equal to that, so it means I can actually find my alpha, if from here now, from the general one, 0.05, I can subtract that and solve for my alpha to be that. When I solve my alpha to be that, then I'm ready to go to the table. So I'm going to write K now equal to that -1. Then I will go to the table. If I go to the table, there's no negative in the table. I will check under the degree of freedom, 14, and level of significance is 0.005. That will give me 2.977. I will be the one that will assign negative. Now, what I'm telling the world that K part is going to be negative. Let me also tell you this. Whatever that's going to be here should be less than what is here, because if you look at it like this, does that make sense? Is there any question on this? Okay, you're all good. Okay, now let's now go into another example. A chemical engineer claims that the population mean yield of a certain batch process is 500 grams, okay, per millimeter of raw material. To check this claim, he sampled 25 batches of, each month. Let me tell you this, investigation follows a claim. Whenever a claim is made, there's going to be investigation. And when we want to investigate, we're going to take a sample. Okay. So, if the computed t-value fall between that and that, he is satisfied with his claim. What conclusion should he draw from a sample that has a mean of 518 grams and a sample standard deviation of that, assuming the distribution of yield to be approximately normal? Now, when you take a look at what I have now, okay, look at the samples, 25, that is less than 30. That's going to be classified as small sample because it's less than 30. Then what do they give us? A population standard deviation? No, you are only giving sample standard deviation. The condition to make use of a T, okay, is when a T statistic is when you are given a small sample size and at the same time you have a sample standard deviation. Now what I'm going to do, here, do you know what I'm using? I'm using formula T equal X bar minus mu over standard deviation divided by square root of n. That's what I'm plugging in. My X bar will be sample mean in the question. The 500 is going to be population mean. There's a difference between sample mean and population mean. The population mean is an hypothesized value, the value in the claim. You can see a chemical engineer claims that the population mean yield is 500. That will be the mean. Okay? And the sample size deviation is 40. The samples, no. So at the end of the day, I got my T to be 2.25. That very T is what we call the test statistic. Now, when I got T to be that, okay, now we now need to be able to go to the table, okay. You know, they say if you fall within T minus T, I needed to pay attention now. You know, take a look at this. If the computed T value, this is a computed T value, 2.25 is a computed T value. If the computed T value falls within that guy, okay, it is satisfied with his claim. Now, what we actually going to do is to now go to the table. If you take a look at this, table F8.4, you know, in the textbook, okay, you go and check under the degree of freedom 24. Why is it 24? Because the sample size is 25. Degree of freedom will be sample size minus 1. Does that make sense? So under the degree of freedom 24, then at alpha level 0.05, it gives us 1.711. Okay, now do you know that if this is 1.7, if this guy is 1.711 at 24 degree of freedom, the negative of it is going to be negative 1.711. Now, which means we are now having between negative and positive. For us to be able to take a decision now, okay, we're actually going to check whether 2.25 falls within. Does it fall? No, because the 2.25 actually greater than that. Okay, and that was why I said the probability of obtaining a T value with V equal to that or greater than that is approximately, okay, is 0.02. So if mu is greater than 500, the value of T computed from the sample is more reasonable, hence the engineer is likely to conclude the process produced a better product than he thought. Now, let me tell you this. It's like we have two hypotheses here. We're still going to do hypothesis testing. It's like we have two hypotheses here. Okay, the first hypothesis that we call H naught, okay, is that is going to support the claim of the engineer that the population mean is 500. Okay, you can see that was the claim. Okay, now another one. Now there are another hypothesis. Okay, another hypothesis is that very mu is greater than 500. Okay, is greater than 500. If you take a look at what we have, you know, okay, to check the claim, okay, you can see that. So what happened now is that and he said, you know, let me see, to check this claim is sample 25 batches. If the computed T value falls, it is satisfied with his claim. Now it doesn't fall. Because it doesn't fall, the computed T value doesn't fall, there is not satisfied with the claim. That's what it means. But we're still gonna talk about hypothesis testing. Okay, but just an introduction. Okay, I think I've explained what is the T distribution used for. Okay, don't forget the central limit theorem puts large sample to be 30 or more. Anything less than 30 is going to be a small sample. So we use T, you know, the T test or T distribution in situation where the population standard deviation is not given and the sample size is small. Okay. Lastly, we're going to go to another distribution called F. I'm not going to bother you about this because you know why? You know, if I have, take a look at this. If I want to derive this guy now, if I want to derive this guy now, okay, F equal U over U is a chi-squared with this as degree of freedom. This is another chi-squared. So F is the ratio of two independent chi-squared. Okay. So, and when when we derive, well, the distribution of F is going to be this. Okay. Now, since U is a chi-square distribution with the degree of freedom V1 and V follow a chi-square distribution with degree of freedom V2, then F distribution, we have two different degree of freedom. Okay. So what do we use F to do? Of course, we use F in statistics, to test hypotheses about equality of the means. Like if you are considering more than two populations, I want to compare means in more than two groups. We make use of F test. So this F distribution is actually what they use to curate values in the F table. Because if I want to take a decision regarding the quality of the means, I need to check from F table, okay, and see whether my computed F fall in the critical region. But we're still going to do all of that. It's just an introduction, okay? So this is the shape for F distribution, okay? It's based on two different degree of freedom, okay? V1, V2 is the degree of freedom. So if I want to check from F table, I will check at two different degree of freedom against the level of significance. That is what it actually means. This is just giving an example here. If I have 6 and 10 degree of freedom, and I want to check under 0. Maybe my alpha is 0.05. Okay, my alpha is a level of significance. Okay, I need to take a look at this. Okay, I'm actually going to check. F is 0.0510,6. That will be 4.06. But if I want to do confidence level, okay, confidence level is 1 minus alpha, right? Which is going to 0.9, all those higher values. So if I want to do F is 0.95 of 610, because there is no this in the table, I'm going to switch the degree of freedom. Okay, when I switch 6 for 10, I'm going to have this. Then I will check under 0.05. Don't forget, what is 1 minus 0.95? That will be 0.05. Whatever I got, I will do 1 divided by that will give me this guy. So they have a relationship. Okay, so they have a relationship. Like I said, I'm not going to pursue that further. Okay, let me stop my share. I'm going to stop my share. And I'm going to share the next slide. So what is very, very important in what we did what we just did is the T distribution. Okay, I'm not going to set question on F. Does that make sense? Please take notes. I'm not going to set question on F. Just going to be T. Okay, so I want to share the second material. Give me 1 second. Now, with this, we are entering chapter 9 in the textbook. I'm going to share that with you really quick, which is going to be very, very crucial in the final, but it's very simple. It's very, very simple, like I said. Okay, I'm going to share that with you really quick. Okay, so I want to welcome you to the new topic. We call this 1 and 2 sample estimation problem, chapter 9. what we just want to do here is when we are trying to figure out the true value of a parameter, okay, so, we don't have resources to study everyone in the population because we're limited by budget. We're actually going to take a sample, and whenever we take a sample, then we're going to be estimating. Okay, so estimation is a process through which we use sample information, okay, when we're trying to understand the true value of a parameter. We now use a sample information, using sample information to make a judgment. Okay, that's what we call estimation. Okay, whenever sample is involved, estimation is involved. When I say 1 and 2, 1 is I may be focusing on one population. 2, I may be focusing on two populations. Does that make sense? Okay, now today I'm going to be focusing on mean, okay, and one population. And let me tell you this. Um, when we're focusing on mean, okay, and if I say single mean, maybe I want to know the average in this university, the average amount spent by student weekly, okay, because I'm only talking about University of Minnesota. That's it. That is one group, one population. Does that make sense? Okay. Now, I'm also going to, in estimation process, we got two types of estimation. We got points, and we got interval. Okay. We got point estimation. Okay. And we got interval. Okay. What is the difference between the two? The point estimation is when I actually have a single value. When you compute the mean, we normally have just a single value, right? That's a point estimate. Okay. But why do we go from point to interval? Is because a point estimate may be wrong or right. And it makes sense to always construct an interval. Okay. Constructing an interval, all values within interval cannot be wrong. Okay, we're always certain that the true value of parameter will lies in the interval. So, and that was why we're going to consider confidence interval when the population variance is known. We're going to construct confidence interval when the population variance is unknown, which means when the population variance is known, the idea of a z-score will be used. When the population variance is unknown, the idea of a t. You remember the t that we just finished? So they got a connection. But let me first come here. I need you to look at the story. This is the way the story goes. If I want to figure out the average, I told you the other time, if I ask 1,000 investigators to go into the same population, take the same sample, they're actually going to have different means, right? Different values for means. Okay. Now, one of the proper, when I say estimator, okay, estimator is a formula that we use in estimation. For instance, if I wanted to get mean, your formula is going to be this, right? The formula is going to be this, right? Now, do you know what? This is an estimator. Estimator is a formula or method that we use in estimation. Let's say, for instance, after getting your mean, maybe you got 60,000, or maybe you got maybe 60. Maybe you are working on average, you want to figure out the average scores of students in a particular test, and you sum the score together, divide by the number of students, you got 60. 60 here is an estimate. Summation x over n is an estimator. There's a difference between estimate and estimator. Does that make sense? Okay, please know the difference. When I say estimate, right, estimator, right? Estimation, they are not the same. Let me start from estimation. Estimation is a process of using sample information, okay, to obtain the value of a parameter. A parameter is a true value. Okay, that process is called estimation. Then estimator is the formula. Whatever formula that we use on sample, that estimator is also called statistic. Does that make sense? Then estimate is the result that you obtain. Does that make sense? Now you can see there's a difference between that. So because I said the other time, this X bar here, when I ask all of you to go into this university, take a sample of 50, you are working on the same thing, your mean is going to be different, right? Now, you know what this guy is now saying? What this guy is trying to say is, when I find the average of all your means, maybe you get a different mean and I find the average of that mean, that will give me what I'm looking for. Situation where that happen, where we're going to say that your estimator is unbiased. An unbiased estimator is the one where the expected value, you can see this guy here, theta cap, this theta cap here is this guy here, is the mean here in this case. Theta cap is an estimator. It's like a formula. Okay. So expected value of that, if it is equal to the true value of the parameter theta, then we're going to say it's unbiased estimator. So that is one of the properties of a good estimator. If I want to figure out the true value of a parameter, of course, if I want to get a true value of a parameter, I need to go to the population, but we don't have resources to study, to interrogate or interview everyone in the population. That was why we conduct survey. Survey is just to take a sample, and whenever a sample is involved, an estimator will be involved because you're going to use a formula. Estimator is a formula. How are you so sure that your formula will do a great job? One of the properties of that estimator is that it should be unbiased. And unbiased would mean when I find the average of different values the estimator can give, and if that can give me the true value of a parameter, then I'm actually going to say it's an unbiased estimator. Does that make sense? Okay. Now I need to pay attention to this now. You know, it can be mathematically proved and statistically observed that sample mean is an unbiased estimator of a population mean. Okay, before going to because the way I'm going to prove this, I'm also going to show that sample variance is also an unbiased estimator of population variance. But before I come into this, and four of us show you this, give me 1 second. You know, if this is the mean that I got from sample, and if this is what I'm looking for, okay, the mean, the one that I'm looking for, this is a population mean. This is a true value of parameter. This is the one I settle with. Then I now want to show the world. When I find the expectation of this guy, then it's going to give me this. How? Let us see the proof. What is X bar? X bar is X is a summation X is summation X over N, right? When I take the expectation of that, you know what is going to happen? Expectation will chase summation away. Okay, so summation, so I'm actually going to have summation over N, right? Expectation of X. Okay, and what is going to happen? When summation is on its own, it's going to turn to N. So N is going to cancel N. What is the expected value of X from statistical literature? Mu. That's how we prove it. That's how we prove that sample mean is an unbiased estimator for population mean. This is a proof. So on Friday, I'm going to start from this. You know what I want to do here? To show you that sample variance is an unbiased estimator for population variance. Okay. Before that can happen, expected value of sample variance must equal to that. So I'm going to walk you through this proof on Friday. Okay. Because, do you know the significance of doing this? Because we know that now justify why we take a sample in research world general, because if the sample mean is an unbiased estimate of population mean, which means sample mean can represent population mean. If sample variance is an unbiased estimate of population variance, then it means sample variance can represent population variance. In a way, we're going to save cost. In a way, there's going to be efficiency. So that is why we do this in research world generally. Okay, I'm actually going to start from here on Friday. Like I said, I'm bringing your exam booklets to this class on Friday, and of course tomorrow you're going to see your grade. Okay, make sure you all stay safe and have a lovely day. Bye for now, everyone.